So good evening, everybody. It is amazing to see this theater full of people here interested in 3D printed ham. On behalf of the Centennial Challenge program, NASA Prizes and Challenges portfolio, and our team, thank you for coming. I think you are in for an amazing treat. This is a celebration of many years of effort in technology development. Hopefully we'll take you through a little journey that is going to explain a little bit about our lunar missions, and most importantly, what we're doing, the challenges, technologies, and what we're doing to gap those challenges and those gaps in technologies. The NASA Centennial Challenge is a program that invites the public to help NASA achieve its mission. And today you're going to be listening for 4 of our finest. They're teams that have participated in the competitions. They are small companies for the most part and a university. And you're about to hear a journey that they have gone through in 5 minutes or less. So it's going to be a very quick journey, but it is an amazing one. And each of them have a website you can go in to get more information. You can come and talk to them after and hear more about where they are, where they were, and where they are now. Truly, I invite you to enjoy this, because it is truly, for us, it has been an amazing thing. Also, we have the opportunity to have with us Alex and Corky today, and they are going to talk a little bit about the NASA mission and the NASA vision and about economics, and because this is about doing things in partnership with commercial. So I was supposed to be here trying to wait for everybody to get here, so everybody's here, so thank you for being with us. Thank you to the amazing Centennial Challenge team that put this together. They are truly an incredible team, and I thank you, because this has not been an easy thing. And you guys enjoy. Thank you to the Space and Rocket Center, by the way. They have been an amazing host, and they'll be hosting us tomorrow also. So thank you to Kay and everybody that made this possible for us tonight, and enjoy, truly enjoy this. It's going to be super cool. So.
Good evening and welcome. My name is Joseph Vick. I'm speaking on behalf of Dr. Kay Taylor, our Vice President of Education at the U.S. Space and Rocket Center. So welcome to tonight's Pass the Torch event at the Rocket Center. It is a community lecture series that highlights Huntsville's historic legacy in spaceflight, and it promotes the current discoveries and future endeavors to come in the Rocket City that will no doubt change the understanding of our place here at home and within the universe. Tonight's program focus is on the challenges and opportunities of building habitations on the moon, and stem from NASA's 3D printed Habitat Centennial Challenge. Moderating tonight's event is Dr. Don Thomas, 4-time shuttle astronaut, author, educator, and champion of the next generation of scientists, engineers, astronauts, and explorers. Inspired by the early Apollo astronauts, many of them from his home state of Ohio, Dr. Thomas dreamed of being an astronaut. A materials scientist, Dr. Thomas began his NASA career at the Johnson Space Center, working as a materials engineer on the Space Shuttle program. In 1990, he was selected in NASA's 13th group of astronauts. He went on to fly on 4 Space Shuttle missions, spent a total of 44 days in space. From 1999 to 2000, he was NASA's Director of Operations in Russia, working at the Gagarin Cosmonaut Training Center in Star City. From 2003 to 2006, he was the International Space Station Program Scientist, directing and planning the experiments performed on the International Space Station. From 2007 to 2015, Dr. Thomas headed up the Hackerman Academy of Mathematics and Science at Towson University, an outreach program to encourage students to pursue careers in math, science, and engineering. Today, he is a professional speaker and continues his outreach efforts inspiring students to reach for the stars. Dr. Thomas earned his bachelor's degree in physics at Case Western Reserve, earned his master's degree and doctorate at Cornell in materials science and engineering. Ladies and gentlemen, Dr. Don Thomas.
Thank you very much. Thank you. Good evening, everybody, and welcome here tonight. I'm so honored to be here, to be part of the Centennial Challenge program. You heard a little bit about them. I had a challenge idea that I presented to Monsi, and that was to come up with a way to make old astronauts like me young again so that I might have a chance to go to Mars, but she just shook her head and said no. But maybe I'm going to talk her into that one. These are really incredible programs or challenges that we've been working on. And just last year, NASA's Centennial Challenges program concluded a 5-year, multi-phase, 3D printed habitat challenge. We had 60 teams from academia and industry across the United States that competed in this challenge. And all of them were, trying to design, the challenge was to design an advanced autonomous construction technology that will need to create sustainable housing solutions for Earth and beyond. And NASA awarded winners a total of $2 million on these challenges from across all phases of the challenge. And I was lucky enough to be at 2 of the competition in Peoria, Illinois. One was about a year ago, and the other one was 2 years ago. And I got to tell you, it blew my mind. Because all of a sudden, it became very real. We're going to Mars. We're building habitats for Mars. And that should be very exciting to some of our Mars generation that I see up here tonight. Because these aren't paper studies. We're developing the technologies, right? Just you? All of us want to go to Mars. But it was really exciting, and it became very real, not just paper studies, but we are getting the technology today that we're going to need for those future missions. And so we have some of our members here from some of the winning teams that will be sharing with us tonight their experiences of what it was like participating in the challenges. So I'm going to introduce them all together. They'll come up one at a time, give a 5-minute summary of their project, and then we'll move on to the next phase, which will be a panel discussion, okay? So let me introduce the first one. We have Michael Bentley, he's the design director of AI Space Factory from New York. Mike, want to stand up? Also, Melody Yashar, co-founder of Search Plus from New York. Melody? Shadi Nazarian, associate professor at Penn State. And Jason Ballard, co-founder and CEO of Icon from Austin, Texas. He says howdy, right? So let's start with you, Michael, if you'll come on up and share your experiences with us.
Okay, hi, I'm Michael Bentley. I'm design director at AI Space Factory in New York City. And we are a multi-planetary design and technology company, and I can say that thanks to NASA and the Centennial Challenge. We're architects with experience designing on Earth. We worked on tall buildings globally, but when we founded our company 3 years ago and we named it AI Space Factory, it was clear that we had this ambition to go to space. We weren't quite sure how we would get there or what the opportunity would be, but that came in the form of the NASA Centennial Challenge and this 3D printed habitat challenge. So right off the bat, this is an incredible opportunity because not only was it about design, but it was also about actually constructing and realizing our idea and concept for a habitat. And as we all know, the challenges of Mars, to be able to construct something using off-grid power, using autonomous construction and in-situ resource utilization so that a habitat can be constructed and ready for astronauts before they arrive. So this is our proposal called Marsha. I think it looks very innovative because we tried to think, we tried to kind of use not our Earth intuition in terms of how you would design a habitat. Usually we think about igloos or domes, kind of like shielding ourselves from the elements and the extremes of the Mars environment and galactic cosmic radiation. It turns out that this is actually an ideal shape for a Mars habitat because it's a very good pressure vessel. So it's like a Coke can. It's very good at containing an Earth atmosphere. And when you're talking about 3D printing, it's very efficient once you've created a small foundation to keep building upwards. And it's also very practical and efficient for stacking different types of uses for the astronauts. So on the ground floor, we have kind of an operations and mission room for the astronauts to do their surface activities. You can see here the double shell structure with a staircase in the distance winding up. So we have this double shell, which allows natural light to filter in. On the second floor, a kind of a kitchen and laboratory area. There's, one of Matt Damon's potatoes by the looks of it. On the third floor, we have astronaut crew quarters, and then finally, which I think is maybe a new feature, a kind of a recreation room. So where we have an Oculus with natural light filtering in, and then windows which look out in all directions across the landscape. So, this is always great fun to envision these projects. And I should say, I think another interesting thing about this project was just the fact of the shape, that to be tall on the surface of a planet is something very human and proud about that. To have this kind of upright stance, it becomes kind of a beacon and a symbol for all of us. And with that in mind, we tried to choose a shape that felt universal and kind of friendly. Having said that, the trickier part of the NASA challenge was that we could not just leave this as science fiction. We had to translate it into a language that could basically be understood by a robot and then printed at the final challenge in Peoria, I think only about 8 months later. And ironically, that was what our first print looked like. We looked to partner with various 3D printing companies, and I think the challenge was just so difficult that it was hard to find anybody, so we had to kind of do it ourselves. So we went to the Autodesk build space in Boston, where we were lent a 6-axis robot. So we basically used off-the-shelf 3D printing technologies, and this was an early construction phase demonstrating the hydrostatic pressure test. So this was a leaky bathtub. So this was not a phase that we won. But at least it got us a sense of how the material works and the speeds, and how challenging it was going to be to print in a kind of a 1/3 scale habitat in under 30 hours at the final challenge. So here is our robot and systems packed up. To get the height of Marcia at 1/3 scale, which is going to be 15 feet, we mounted this 6-axis printer to the front of a forklift. And here you can see it printing. And I think at this point, this is kind of an interesting transition because it starts to really showcase the decisions we made in terms of the material. We opted not to go with the concrete. We felt that on Mars, water would be such a scarce resource, and also that in the very, very cold atmosphere, it would have a tendency to sublimate if it was part of a concrete mixture. So we opted to go with a biopolymer and basalt matrix, or a basalt compound. And it was a bit slower. It was actually a lot slower than concrete. We only barely finished, but it was very, very precise and very, very accurate and very, very clean. So you can see here, to strategically be able to print within the 30 hours, we had three layers at the very base, then 2, and for I'd say the last 4 or 5 feet of the habitat, it was only basically a 3/4 inch wide bead just layered on top of each other. So it was very, very precise. And then we were able to autonomously place all the different components of the habitat, including the Oculus. In retrospect, if we'd had a bit of foresight and made it an inch bigger than the design specs, it would have sat nicely on top of our slightly short structure, but it fell through. So we failed the airtightness test, but we passed with flying colors in terms of autonomy, and that's because of this material. It was very, very clean. The process is basically just melting this biopolymer inside a barrel. If the print ever had to be stopped, it was very easy to reheat and continue to print. And not to speak on behalf of Penn State, but I think you can see the difference between our little area, which was almost empty, and then the amount of equipment required to kind of run a concrete operation and the challenges with it seizing up the lines, I think was what in the end enabled us to do quite well in terms of the autonomy points. And then the other great benefit was that the stuff is incredibly strong. So this is looking down and seeing that this, I think 96-ton Caterpillar was actually lifting off of its tracks, trying to put a dent in Marcia and wasn't actually able to make any impact. Having said that, eventually it had to be demolished. And I think this was a kind of another really profound moment in our journey, where we thought, well, what next? We've completed this challenge, and we found out that we're incredibly proud that we won this final construction phase. But we had Marcia in ruins, and thinking, okay, well, what can we do next? And this is what I describe as our own kind of overview effect. I read a quote from Michael Collins, the Apollo 11 astronaut, who said that looking back at Earth, you realize that it's tiny, shiny, beautiful, it's home, and it's also fragile. And I think this was this kind of moment where we thought, well, we have this incredible material, and because it's a bioplastic and it incorporates basalt fiber, we can actually recycle it. And we can also use everything we've learned about printing on Mars, hypothetically, to address construction issues on planet Earth. And so with that in mind, we decided to take all those components of the Marcia shell, grind it up at a facility, and we're going to transform it into Terra. And so Terra is basically like Marcia's cousin on Earth. So this is a kind of an eco-habitat, built using this space technology. We're printing it near New York City. And the idea here is that by using a biopolymer, which we can grow from corn, we can also incorporate recycled plastic if necessary, and we're sequestering carbon as we're growing this material, we can really start to disrupt the construction industry, which, as we know, is actually a huge polluter. So I think concrete alone is responsible for 5% of global carbon emissions. And our vision is that you could actually start to grow these materials and really reimagine the way that we build and live on this planet. So this is Terra. This is what we imagine it is going to look like at our site, which is on the Hudson River, about an hour north of New York City. West Point Military Academy is just in the upper corner of the screen. We did an Indiegogo campaign, which was inevitably a huge success. We booked I think 400 nights in a matter of months. The other great thing about this was that it enabled our followers to kind of reach these funding goals. So for example, we were able to get a hydroponic garden inside the habitat. We also are providing solar panels. So it's a double shell, a lot like Marcia, although a bit smaller. And on the inside, you have a small kitchen, living quarters, and then kind of encased in a spiral stair, a small office on an upper floor, and then a sleeping platform which will be hanging out kind of underneath the oculus. And then tucked in under the stair, kind of a Japanese-style bath. And so this is us at the end of the summer. So this is the same robot, Mobi 3, which was used in Peoria, arriving somewhat haphazardly. It turns out that after you add several tons of counterweight to an industrial robot, it doesn't like hills. But this is arriving on the site. And now we're kind of tackling the challenges of actually creating a building that is 3 times the size of Marcia. So this print, I think, set the record for the tallest kind of polymer structure. And we're trying to create something that is 22 feet in diameter and 26 feet tall. To do this, we're actually building a turntable. So the robot will remain stationary on one side, and the whole building will turn, and we'll be able to print up one side to get the height. So here we are. This is Mobi and the robot doing we call these its stretching exercises before printing, getting up to its full kind of 26-foot high reach. So to conclude, I think this is such an incredible journey for us, but as I said, we are a multiplanetary, we want to be a multiplanetary company. And so we're totally committed to this long-term vision of going to the moon and Mars, but as we all know, it's a very long trip. And there's many, many stages. And I think what's important is that we all find ways to kind of be able to push our ideation and our technology research on our own planet. So, we've presented MARSHA, which clearly, if you work with NASA, you have to have cool acronyms. So MARSHA obviously stands for Mars Habitat. Terra, in fact, stands for terrestrial analog. So it's a way that we can find ways of testing space technology and promoting autonomy, in situ resource utilization on planet Earth for the good of both planets, hopefully one day. So this should be finished sometime in the summer. I hope you will all be able to come and visit us. Thank you very much.
Thank you, Michael. Excellent. Okay, for next, we'll call up Melody. Will you come up and join us?
Okay, hi. My name is Melody Ashar. I am a co-founder of what I like to call an applied research practice called Search Plus, which is short for Space Exploration Architecture. We are a small group that incorporated as a direct result and product of the Centennial Challenges program. So we were in an informal group of students and also academics who had met in 2015 at Columbia University, and we could have never really imagined what would have resulted from our winning the 3D printed habitat challenge in that time. So since then, we've been very fortunate to collaborate with private aerospace companies and the likes of United Technology Aerospace Systems, now Collins, Virgin Galactic, and a number of other universities, Carnegie Mellon, Pratt Institute. And it's really thanks to our success in the Centennial Challenges program that we've been able to grow and we've been able to see ourselves succeed in the way that we have. So our mission statement, if we were to have one, and that we really, what we aspire to do in the work that we've done, is to conceive, investigate, and produce innovative human-centered designs which enable human beings to not only live, but to thrive in space environments beyond Earth. And so what we do in order to achieve that goal, in order to achieve that vision, is we develop human-supporting design concepts for living in space and space exploration. Our core group, myself, and our background tends to be in architecture, industrial design, human-centered design, human factors, but in order to come up with the proposals and the projects that we have in the last 5 years, we collaborate with a group of subject matter experts, which ranges from planetary geology to ISRU subject matter experts, structural engineers, and the list goes on. Our original network just started as friends and people who we were cold calling when we first started out in putting together our original proposal in the Phase 1 challenge. And since that time, the caliber of our consultants and the people who we collaborate with has just gone up and up and up. And it's been incredible as a journey and as an experience to witness. So these are some of our habitation projects. I'm going to tell you about 2 of them today. One which was the Phase 1 winner in the 3D printed habitat challenge in design, and the other which was the Phase 3 winner in final design. So I can safely say that we've won both of the design solicitations for 3D printed habitats over the course of the Centennial Challenge program. So these are our projects, our habitat proposals that we submitted over the course of the challenge. And we participated in Phase 1 with our winning proposal, Mars Ice House. We didn't participate in Phase 2. And then in Phase 3, we won in final virtual design for Mars X House. So I'll be telling you a little bit about those 2 habitat concepts today. We also collaborated with APIS Core over the course of construction level 1 and construction level 2, and we're very lucky and fortunate to have won both of those levels as well. So that's us winning on the left in 2015 and us winning on the right in this past summer, 2019. So this problem of 3D printing a habitat in outer space on the moon and Mars, what's it going to take? How exactly are we going to approach this? What are the foundational principles for 3D printing a habitat on the moon and Mars? The most core principle is going to be one that's referred to as in situ resource utilization, ISRU. And what that means is that we need to take advantage of the local and indigenous materials on the planet in order to come up with the material system which will actually construct the habitat. It's going to be prohibitively expensive to launch all of our materials, so we want to be able to use everything that we find there that is local to the planet in order to construct infrastructure in our future settlements. The next thing that we're going to have to do is we're going to have to prepare our site. We're going to have to validate that the materials and the resources that we want to use are actually the ones that we find. We'll have to excavate the site to collect those materials and make sure that they're stored properly for us to actually use when we're 3D printing. And then finally, our robotic systems will have to deploy, and the habitat itself will be 3D printed through some kind of autonomous means. So in our approach, given that we come from a design background, what we attempt to do is synthesize engineering constraints with human factors-driven design innovation. And from our perspective, this has been our secret sauce in the approach that we take to the habitats that we have designed and that we've introduced. We're really looking to synthesize those constraints in a way that makes sense, but also introduce innovation from a human perspective. So Mars Ice House, as I mentioned, is the first prize winner in the Phase 1 Centennial Challenge for a 3D printed habitat. What we did in Mars Ice House was we introduced a clear ETFE membrane to act as the pressure vessel for the entire habitat, and then introduce an ice shell that would be 3D printed on the inside. The entire habitat would be surrounded around a vertically oriented lander, which would house all of the mechanical components as well as the ECLIS, the environmental control and life support for the habitat. Why did we choose water ice? This is a pretty unconventional building material choice. We do know, and we now have evidence, of course, that there is subsurface ice even a few centimeters below the regolith surface on Mars. So from our perspective, if we're going to introduce a sustainable long-duration mission on the surface of Mars, mining for water ice is going to be critical to that, both for all kinds of other ISRU purposes, but also for the health and sustenance of the astronauts. We also know that water is a more effective radiation shield than both regolith and aluminum. So this was something that we wanted to really capitalize on in protecting and ensuring the health of our astronauts. We introduced a vertically oriented hydroponic greenhouse that would be growing off of the lander itself, and then the crew quarters and other program elements would be encased within the ice and 3D printed within the ETFE membrane. We were interested in the possibility of introducing translucency through the ice shell, and thanks to some work that we were able to do a little bit later on in collaboration with Lamont University, we were able to validate that we could actually achieve adequate translucency through some initial tests that we did in order to actually achieve a kind of vision window through the ice. Here's a model of the ice house that has been exhibited internationally that we're really, really proud of. And very fortunately, the ice house concept spun off into another project in collaboration with NASA Langley, Mars Ice Home, which was not a 3D printed structure, but actually a filled and frozen ice habitat concept that we were able to develop over the course of a number of funding rounds with a group at NASA Langley. This also spun off into the Big Ideas Challenge, which was a challenge that we collaborated with to organize and host with NASA Langley as well. And so Mars X House is the final winner and final design for the Phase 3 competition, which ended this past summer. And instead of a water ice habitat, we introduced a regolith-based concrete for the design of this concept. We introduced a hyperboloid form for the structure itself, recognizing that we needed to contain a tremendous amount of pressure on the inside for it to be a shirt sleeve environment for the astronauts. But we also introduced a water bladder at the very top in order to contain the pressure that would be pushing upwards and outwards. One of the things that we really strive to do is to demonstrate what it would be to live within these habitats, what would be a day in the life, what it would be like to actually experience the habitat as a person, as an astronaut on a future long-duration exploration mission. So these are some of the ways that we've imagined the future crew living within the habitat itself. Some of the other things that we had to consider when putting together this proposal was the material system as well as the deployment system for the actual construction of the habitat. So in putting this proposal together, we came up with, we introduced a high-density polyethylene inner layer and introduced a number of reinforcement mechanisms so that the concrete would actually contain the pressure and introduce adequate tensile strength. And then, of course, the regolith concrete would be 3D printed on the outside. And then finally, in putting this all together, we were integrating building information modeling software methods with a construction sequence to actually demonstrate how this would all work together. So which materials would be printed first, in what sequence that would happen, what kinds of robotic emplacement would need to happen over the course of the printing process, and how these systems are all going to come together. And here's a model of our X-House, which is also now being exhibited internationally. So to conclude, some of the leading, I guess you could say, themes and research elements that we've been thinking about consistently over the course of our participation in the Centennial Challenge and over the course of our work since we started in 2015 have been about new ways of thinking about construction technology, new ways of thinking about materials that we can use for deployment on the Moon and Mars, but also here on Earth today. And then finally, how we can introduce new ways of living in outer space, new ways of living extraterrestrially that will enable us to thrive and not only just survive on another planet. And thank you.
Thank you, Melody. Thank you, Melody. Next, we'll invite Shadi Nazarian up from Penn State.
Thank you for the opportunity to speak. So we were very aware of the problem that we're facing, a crisis on Earth where there is a growing population but lack of affordable housing. On Earth, there has been two extreme ways of dealing with this. One has been to have favelas, the picture above, that you could see in Brazil, for example, that are without order, there's no infrastructure, and they're unplanned, but they're very vibrant and pleasant. And the second one is a housing created very regularly, very ordered, but they all look the same, and they're not very pleasant to live in, but there is infrastructure available. So we made it our mission to pay attention to and achieve United Nations Sustainable Development Goals, to advance construction technology on Earth, and to address mass customization rather than mass production. We had been interested and continued to develop new materials and systems for 3D printing at large scale, and began to notice that the whole process really affects the process of design. So this is all prior to the competition. I was working on a seamless transition between geopolymer concrete and glass. I was thinking, what if we can seamlessly transition from concrete to glass gradually, so a graded transition, so that we could have structure where we need it, thermal capacity, because concrete is actually porous there, but when you unite it with glass, it becomes a porous material on the inside, but it's sealed on the outside. So we were able to achieve that with some colleagues at the university, Penn State University. We have a very strong material science and engineering department. So we had achieved this already, and we knew that it could happen at laboratory scale. We have achieved it. And on the other side of the ocean, my now colleague and research partner was thinking about graded transition between concrete and cork. And they were interested in the thermal capacity that that would bring. So we actually printed that. And we know that we could print and gradually have more and more granules of cork where we need more thermal capacity. Back to the glass to concrete. You can see on this corner an image that is taken that shows where there's heat loss all around the windows. And so one of the things that going seamlessly from concrete to glass makes possible is to avoid that heat loss. So we began our participation at the competition with the strategy to explore what is possible through 3D printing. We know that 3D printing would enable us to do things that we wouldn't be able to do with the current technologies. One would be the seamless transition from one material to the other. Secondly, we would be able to print so precisely so that we know exactly where to have the structural response to the structural needs, and where there's thermal need, and also where we need transparency. So if you imagine in a wall, you could gradually transition from concrete to glass. When we began participating in the competition, we had not really 3D printed before, and our group was a few faculty full-time teaching in subjects completely not related to 3D printing. So it was just personal interest. And the team grew. We now are 6 faculty, and at any time, some students who are interested would assist us, and their work begins to focus on this technology. So this phase, we began in phase 2. We didn't know about phase 1. It was the competition was very well organized. It enabled us to actually understand this technology because of the stages that were coming one after the other. So these are the structural member competitions from a fragment of a column to a fragment of a beam to finally a dome, where we got the second prize at the head-to-head competition. This is the third phase we also participated in. And the hydrostatic test on the upper left corner is shown here. And on the right lower corner, we have the freeze-thaw test that was required by the competition. And on the upper, the automated processing of and placement of hatches, for example, and reinforcement units. At the same time, our research was obviously affecting our pedagogic goals. But that was in addition to our full load of teaching. So it was our interest, so the students were interested to join us and learn. But it enabled us to achieve more complex surface conditions that you could see on the upper right, and precision in achieving that kind of double layer surface condition where you could have, for example, plumbing or whatever services needed in between the layers. We were testing also shape accuracy. On the lower right, you can see an exercise where we go from a square, and on top it becomes a dome enclosure. That was one of our main goals, to be able to enclose a structure using only this technology. So what is known in architecture as corbelling techniques, we began to use and to be able to bring it into our design. We participated in the virtual design competition and the actual design competition. Our virtual design competition, we proposed going gradually from concrete to glass on top to bring light in. And in the walls, we knew that in order to be able to prevent the cold coming in, we used the gradual transition to cork. So we had tested already, and we knew that what we were proposing is within reach. And then we have the BIM platform that we used as a framework to unite everything, to generate the parametric design, to do all of our analysis, environmental and structural, and to optimize many different things within the same platform, but also do the simulations. So there were challenges, of course, in making this happen, in the systems, in the development of materials and all that. And we were able to overcome those challenges, but it was very difficult because of the way concrete behaves. But we selected concrete because we knew that all the ingredients are available on Mars, infinitely available, in fact, and with much less processing required. So it is a realistic vision. We were able to reach our goal of producing a structure that is enclosed totally using this technology without any support, structural support on the inside. And here is our team of faculty and students. That's it. Thank you.
Thank you, Shadi. And last but not least, Jason, come on up.
Yeah, I'm a Texan. It turns out, for those of you who didn't know, the Texas to moon ratio is 50-to-1 surface area, and the Texas to Mars ratio is over 200. And these are excellent scores compared to the other states of the United States. And for this and other reasons, are we there? Great. For this and other reasons, I think the moon and Mars are very compelling endeavors. What I'm going to do, for those of you who like a roadmap, and NASA likes roadmaps, I'm going to spend 2 minutes telling you about ICON. I'm going to spend 2 minutes talking about the Centennial Challenge. I'm going to spend 2 minutes talking about what's next. So let's see how I do. So why does ICON exist? There's this global housing crisis. You can Google it. It's terrible. It is existentially urgent that we find a way to shelter ourselves, all of us, with dignity, without ruining the health of the world that we occupy right now. We've been building buildings the same way for 1,000 years, no joke. If I sent you a picture of a house built in 1020, it's nails and sticks and bricks and mortar. And it's time for the construction industry to join the modern world, which is so clearly automated and digital. So ICON started as a company with its feet kind of planted firmly on Earth. So the kind of questions that get us out of bed in the morning are, what if you could download and print a house in 24 hours for half the cost? What kind of problems could you solve? What kind of opportunities could you create? Because the promise of 3D printed homes is that they are faster. We haven't announced this yet, so you're getting to hear it first. We recently printed 3 houses at the same time with 1 printer, and we averaged 24 hours a house. Infinite customizability. So all 3 of those houses I just told you about had 3 completely different floor plans and were printed at the same time. It's a naturally high performance material, very resilient, high thermal mass, et cetera. All of this lowers the cost both of construction and of operations. If it's robots and software, it's scalable. And waste. If you've ever been to a construction site, sometimes there's more waste than house. And with 3D printing, you print what you need to the drop, and then you stop. And that's cool not just because it rhymes, that's cool because that's a big problem. And so we're a construction technology company. We work in robotics, software, and advanced materials. I'll tell you a little bit about that in a minute. And we use all that to print buildings. We have delivered more 3D printed buildings on Earth than any other organization so far, and we permit all of them according to local building code, including in seismic areas. This is about a year-old house, so this doesn't even represent current state of the union. All of you would live in this house. This is our current, for a little bit longer, state-of-the-art printer. It's called the Vulcan 2. Can print houses up to about 2,000 square feet. It loads and unloads right off a standard shipping trailer and can start printing within an hour after arrival. It's operated by the world's first robotic operating system for construction. It's tablet and phone-based. You can see that is not an engineer. That's a gentleman named Connor who a month before had never dreamed he'd be 3D printing houses down in Mexico, and he's using his iPhone. The material we're using, right, super strong, super high thermal mass, very long lifetime. This is beginning to be the kind of improvement we need to see on Earth because we love going from science fiction to science reality. So this is what we pitched a customer that we could do, and a few months later, this is what we did. Again, what we could do and what we did. And so this sort of sensibility at Icon of like, we're the company that goes and does the things has influenced the way that we approach our work with NASA. This is the Vulcan 2 out in the field, printing 3 houses at the same time, another perspective. And this is our small but salty team. We like what we do. And so we're really excited about the progress we've made on Earth, and we think the experiences of actually getting out there and printing houses have informed the way that we've approached this challenge. Because as I said, we sort of had our feet planted on the ground, but I think I'm preaching to the choir here that I believe, and I think a lot of people in this room believe, humanity will either become a spacefaring civilization or go extinct. And so I like the former rather than the latter. In 2017, before I actually ever 3D printed a house, I became a graduate student in Space Resources program at the Colorado School of Mines. We partnered up because Icon was very busy and the School of Mines needed some help to participate in this NASA 3D printed habitat challenge. But for a little bit of, somebody brought up ISRU, and I think it's an important point to make. I'll use concrete as an example. Why in-situ resource utilization is so important and why I think NASA is so interested in this technology. Getting a single bag of concrete into low Earth orbit using our very best reusable rocket technology would cost $75,000 a bag. To extrapolate this from this house, this was the first permitted 3D printed house in America. We did that with Vulcan 1, our first printer. To get just the dry mass from that print into low Earth orbit with a Falcon 9 rocket would be $55 million. To get that same dry mass into low Earth orbit with a non-reusable rocket system is about $500 million. The new lunar landers haven't been developed yet, so I don't have those numbers, but order of magnitude estimate, to get all the dry mass to the moon, you're talking about $1 billion a house. And that makes Manhattan and San Francisco real estate look like a steal, but I don't think it's going to be the kind of thing that U.S. taxpayers are excited about paying for. And so we entered the Centennial Habitat Challenge because we agree with NASA that we've got to do a better job of ISRU if we want to become a spacefaring civilization. We donated our Vulcan 1, or another Vulcan 1 to the Colorado School of Mines, and we just let the undergrads have at it. So we entered the challenge with undergrads in the first version of our technology. But it was fun to start putting it through its paces to see how it compared, because we weren't sure if this, we were there to learn and experience. And what we learned is that sure enough, this can be done. You guys have seen some great pictures of the other people who participate in this challenge. This has legs. Like this will work. And then on the design side, we started taking everything we've learned from actually printing houses on Earth and putting those constraints into our design. So our goal was to actually develop designs we could print like with current state of technology. I think it's interesting how everybody kind of got this more vertical rather than the traditional dome structure. We sort of also landed there. It's easier to print and maximize the usable square footage. We also had this kind of like this modular approach where you could sort of add on quite easily. And so we got to the end of this project and we said, this is a real viable application of this technology. And in fact, I'm a biased voter here, but we think this is exactly the kind of path NASA should be chasing down. And I think NASA thinks the same thing because this Centennial, the work didn't stop after the challenge ended, which is so, so cool. In the meantime, NASA has said through the Artemis program, we are going back to the moon on our way to Mars, and we are going to stay, not just boots and flags, but we're going to put a permanent infrastructure on the moon. I think this is very exciting. I think it's going to be an excellent engineering proving ground. I think it's going to be an excellent science laboratory. And more romantically, how incredible that humanity's first home on another world will be something we can like I can't like look up and point at it. I think that human element is like very important for us to believe and understand that we're a spacefaring civilization. And so we've started in partnership with NASA and in partnership with some of the folks who you've heard from tonight. We've kept at the work, and we've begun thinking about the lunar environment. And it turns out, if you don't want to build billion-dollar houses, and you want to start using locally sourced materials to build locally delivered buildings, with software designed for the specific needs, and you want all this to be economically viable, then 3D printing is your best bet. Now, listen, it's going to be really, really hard. I think it might be harder than landing rockets. This is going to be a really, really hard task, but we need to do it. And it ain't going to just be buildings. First of all, we got to figure out landing pads. I was at the Lunar Dust Symposium in Houston last week. The lunar landers from Apollo, the exhaust, propelled rocks, and lunar dust, which is nasty stuff, by the way, at speeds in excess of escape velocity, which means like landing a rocket on the moon is a global event. The dust literally goes all over the entire lunar surface faster than a bullet. And so if we don't want to be spraying our new moon base with machine gun fire repeatedly every time we land a rocket, we've got to get landing pad infrastructure. Similar for roadways, we cannot be kicking up lunar dust all over the place. And eventually we need sustainable, resilient habitats, not tin cans, not blow up tents. If we want to stay there for a long time, we need to build resilient, long-term infrastructure. And we need a technology that can do all these things all at once. And we think it's additive construction and 3D printing, and that's ICON. Thanks for letting me be here. This is a dream.
Thank you, Jason. So who's ready to live on Mars? Good. We're taking names here tonight. Hey, you just heard of 4 of the teams of the 60 that we had competing in this challenge. I think it was really incredible, the technology that you've seen. And on behalf of all of NASA, I want to thank the teams here and let you know we are so proud of everything that you've accomplished, and we look forward to see what you're going to do in the future as well as we continue this journey to Mars. It's a tough road going to Mars. This isn't going to be easy, but with your help and your enthusiasm, which came across loud and clear here this evening, I think we're going to get to Mars. So let's give them a round of applause once again. And with that, we're going to shift gears now and do a short panel discussion. So I want to bring up Dr. Alex McDonald. He's NASA's chief economist from headquarters. Why don't you come on up here, Alex? And Dr. Raymond Corky Clinton, associate director of Science and Technology Department at Marshall Space Flight Center. So why don't we just start off briefly, maybe tell us a little bit about what each of you do here at NASA.
Yeah, sure. Well, first of all, it's just a great pleasure to be here with everyone. I feel kind of sad to be one of the suits following these kind of 4 incredible innovators and entrepreneurs out there. That's the kind of stuff that actually, everything we do in Washington, D.C. is geared to enable, right? It's to enable us to kind of develop these solutions, inspire people to kind of develop new solutions, and I think the 3D printed Hab Challenge has been a great example of that. I serve as the chief economist at NASA headquarters, and what that mostly means is thinking about how to allocate our scarce resources within what's currently, about a $22 billion budget from the recent appropriations bill, but the president has also just put out his most recent budget request, which would, if appropriated at that level, would be about a $25 billion budget. This is one of the strongest budgets NASA's had in many decades. It's incredibly exciting, and so part of the challenge as an economist is thinking that, well, as incredibly generous as that is, and how incredibly lucky we are to have it, it still doesn't quite pay for all the incredible things that we want to do in the future. So we got to think about how to be cost effective. We got to think about how to working with private industry, and we got a huge number of programs around the agency and across the country. Centennial Challenge is just one of them, and I spend my day trying to think about what we can do to help.
Very good, thank you. How about you, Corky? Why don't you tell us about what you're working on?
Sure. I work in the Science and Technology office at the Marshall Space Flight Center, so I'm a local guy,
closer.
and I'm. Pardon?
A little closer.
Is that working better? Everybody here now? Yes? That's all good. So in the Science and Technology Department, we've got over 50 programs and projects that we get to look over, which means we have an incredible opportunity to look at a diverse spectrum of things. And to be honest with you, one of my favorite things that I'm working on right now is additive construction, working with the folks that you just heard about for the next generation, which we hope we'll be able to do on the moon. And then in addition to this, which is my particular focus, we house all of the different science disciplines that NASA has. We've got astrophysicists, heliophysicists, which means they study the sun, planetary scientists, and earth scientists. We also house a couple of level 2 offices, which means they help as mission managers and provide oversight to the planetary missions. You may have heard, I'm sure you've heard of the New Horizons that flew to Pluto. Probably saw some pictures of that, OSIRIS-REx, which hopefully will bring home some material from an asteroid, other projects like that, as well as the Technology Demonstration Missions. That's another level 2 office, TDM, and they're also developing technologies that will go to the moon, like solar electric propulsion, cryogenic fluid management. So we're all now focused on going to the moon. Even our technologies, the moon and Mars, things from in-space manufacturing, in-situ construction, nuclear electric, nuclear thermal propulsion. All of the focus now is shifting on to the moon and then beyond to Mars. So it's an exciting time and it's an exciting place to work.
Thank you. You know, the current schedule has us landing on the moon in 2024. And this isn't just a one-shot trip to the moon again. We're looking to have a sustainable presence on the moon. So I want to ask each of you to just answer, briefly, from your perspectives, what are the largest technology gaps for developing a sustainable lunar presence? Maybe just the top 2 or 3 that you can think of.
First of all, the agency has study teams that are out there looking at that. So within the end of the year, we'll have the technology gaps identified and strategic development capability plans looking at how we go solve those. But from my perspective, you heard them talk about going and living in sustainable presence on the moon. Living and working there, you have to use the resources that you have. You have to live off the land. So to me, what do you have when you have the resources? You've got regolith and you've got water ice. So we've got to learn how to use the regolith. That's, I think, one of the biggest challenges, but in multiple areas. Jerry Sanders said in one of his papers a few years ago, when he cited some of the uses of regolith and their construction, obviously, there's manufacturing and there's consumable production. Shelter, water, oxygen, which we've got to bring with us, just like the explorers of old did, and food. And we'll hear later that one of the challenges that we're looking at now is nutrition for the moon. So I think that's the greatest challenge and the highest payoff for what we have to do on the moon.
All right, thank you, Corky. Alex?
As an economist, I tend to go with, reliable, safe, and affordable access to lunar surface. If we're going to sustain this, it's going to be because the nation is both able to and willing to keep sustaining the activity. And currently that's predominantly a function of national appropriations, which thankfully right now are very high. Now, if we're able to do lunar activities with lunar landers and launch vehicles that are in that budget profile, which we're currently planning to do, then I think we're going to be able to sustain that. But having them be affordable and sustainable is going to be key. I mentioned the most recent budget. It is indeed the highest in nominal dollars, but as an economist I have to point out, it is not quite the highest in inflation-adjusted terms. It was quite higher in the mid-1960s. And that level turned out to not be a sustainable level of national appropriations. And so that technology, for me, has to encompass the economic accessibility and the reliability to allow the nation to keep doing it, and indeed to have our international partners use it, potentially be willing to afford to pay for it, to have private individuals potentially being willing to afford to pay to do it. So I think that's a key set of technologies that encompass the transportation system at a lunar surface. And the other one then is, of course, long-duration human spaceflight. Obviously, there's long-duration technologies for ECLSS that you need on the surface, but one of the key parts of Space Policy Directive 1 that the President put out is the idea that we're going to use the moon and have a sustainable program of exploration that goes on to Mars. And one of the key ideas is to use the moon as a proving ground for the technologies and systems and operations that we're going to take to Mars. And we know, I mean, you know, depending on how you want to look at it, right? Opposition class, conjunction class, you're talking 2 to 3 year missions either way. And so that's a real serious ecosystem, especially when you don't have a lot of resupply opportunities. So for me, those are the two: reliable, affordable access to the surface of the moon, and then figuring out our long-duration ECLSS and overall habitation system needs.
Very good. And you both have different perspectives on this and different backgrounds, but can you talk a little bit about the way you view the public-private partnerships and their value to NASA in achieving sustainable lunar presence?
Yeah, I mean, I would just say absolutely critical. I mean, you know, I've been at the agency for about 12 years, and I started out at NASA Ames, and, you know, back in 2008, and folks here, you know, at Marshall, because I know how Rocket City works, and we got a lot of legends in the room here tonight. People have been, you know, on this path for a long time, too. It wasn't always easy to think about public-private partnerships and have the agency put that at the forefront. And now it really is. You know, you can go back to some of these old documents that I was privileged to work on, like the Emerging Space Report, which was about how essentially going out into the future for decades and centuries, we hope, it will always be both private individuals and the government working hand in hand to achieve our collective ambitions in space. And right now, that is true for every major development program we're engaging in. That is core to HLS, it is core to Gateway, and it is absolutely, of course, you know, core to Commercial Crew, which is going to be, personally for me, the highlight of the year. So I think right now we're in an incredibly fortunate time where, you know, the agency has kind of turned the intellectual corner, so to speak, and sees collaboration with the private sector as just critical to how it does business and everything. Centennial Challenges is one of those, a different way of doing it, and I think it's going to be exciting to see how that grows and evolves.
Very good. Corky.
Yeah, I'll pile on. I completely agree with that. And yes, the agency has turned the corner. And yes, public-private partnerships are critical. The agency is literally working with dozens of companies across the U.S. in areas like architecture studies. They're also designing new systems. They're developing new technologies. They're testing the systems and the components, getting ready to go back to the moon. Alex mentioned the human lander. There are other things that the agency is interested in. Pressurized and unpressurized rovers. There's the Next Step program, which literally has the term partnerships in its title, Space Technology Exploration Partnerships. Things we're looking at there: in space manufacturing, in situ resource utilization, waste management. Then there's the Tipping Point program, and that's particularly to help industry partners that are very close to being able to commercialize a system that, with a little bit more funding from NASA, they can sort of get over that technology valley of death and commercialize a system. There we're looking at things like increased rover mobility. We're looking at advanced avionics, and we're looking at cryogenic fluid management. So there are areas all across the spectrum, spacesuits included, the habitation and gateway logistics service provider. All of those things are looking at being done by partners with NASA. So it's the entire spectrum of the research activities and exploration activities.
It's critical for us getting there.
Absolutely.
Yeah. Corky, one other question here. Could you just briefly mention what role your directorate, the Science Technology Mission Directorate, is playing with respect to NASA's mission to land humans on the moon in 5 years? What are some of the key things you're working on, maybe 2 or 3?
Okay. STMD is working on precision landing to make sure that when we land, we've got a safe place to land. They're working on cryogenic fluid management. But the other thing they're doing is sending out these CLPS landers, which are commercial lunar payload services. And these are all done by private companies who've bid to take payloads to the surface of the moon. There we're going to take scientific instruments that will study the surface, help inform us about the materials that are there when we're talking about living off the land. And we're going to take technology demonstrations. And all of these missions, they start in 2021, and they plan to have 2 a year ever after to go to the surface of the moon. So with this body of knowledge, what STMD is doing is trying to prepare the way for the human exploration when the humans finally get to the moon.
Yeah, exciting stuff.
It's very exciting.
Alex, one final question for you. From an economic standpoint, what does sustainable space exploration look like to you?
Yeah, I hate to belabor it, but continued high national appropriations. So, thank you everyone who pays their taxes. You know, and I don't want to, so it's a bit of a joke because, you know, obviously that's kind of where we are, but I do want to take a moment and just recognize how amazing this is. So my work was in the economic history of space exploration, okay? And I spent a lot of my time working on a book that took me way too long to write called The Long Space Age. And what it was looking at how we funded astronomical observatories in this country long before NASA even existed, right? And my favorite example is the Cincinnati Observatory, which was built in the 1840s. And it was because a guy named Ormsby Knight Mitchell, which is a fantastic 19th century name, comes to Cincinnati and says, you know what, these Russians, they got a real big observatory over in Pulkovo. Well, you know, we're a Republican country over here, small R Republican, you know, and, you know, we don't have a king. We don't have a queen. So we don't have someone to build us a big telescope. So here, in America, the people are going to have to become the patrons of science. And he collectively went down the street, got everyone to pitch in their money, and they didn't quite build the world's largest telescope, but they did get money to import the third largest refractor in the world from Germany. And for a brief period of time, the citizens of Cincinnati in the mid-19th century were able to look through the telescope, not the scientists, mind you, the citizens, the people who paid for it. And they'd funded one of the world's largest observatories. And John Quincy Adams, the only president who was president and then returned to the House of Representatives because he considered it to be a higher honor to be a representative of the people than just a mere executive, he made his last journey of his life to give the dedicatory address. And he, you know, said that that is how we're going to have to fund science going forward. And to this day, thanks in part to a lot of people's efforts in this audience, I know, that is why we have the greatest space exploration program in the history of the world, because it is funded by the people, and we're very lucky to have it, and I hope it only grows in both achievements and appropriations.
And I'll tell you, I travel around the country, and young and old, people support our space program here as strong today as when I was a little boy watching the Apollo program ongoing. There's great, great support across the country.
And it's growing today again. Absolutely, we're seeing that in the polls.
Would you guys be willing to take a few questions from the audience? Absolutely. Why don't we, anybody here have a question you'd like to ask tonight? Yeah, why don't you stand up if you could yell it down nice and loud? Hold on a second. We'll help with this.
And you can get me in trouble, just not too much trouble, okay?
So I'm actually doing some research of my own where I'm looking at stuff like using expected net present value for doing space mission architecture decisions. And I know that we are a government space agency, so we have to follow the directions of our leadership. How much can we leverage decision-making economics to say we should go do this way versus we must do what the politicians tell us to do?
Well, I mean, one of the great things I've always thought about, especially at the centers, right? I mean, you know, the job is to do the research and to show people what the analysis says. And for many years, you know, funded a lot of studies that suggested that we're going to need to think about, you know, sourcing propellant from other places than the Earth. Now, of course, those studies will also show you things like the fact that extraterrestrially sourced propellant becomes less competitive the cheaper your launch costs get from the Earth. Right? So there's a lot of dynamical relations there, but one of the great things I love about NASA, why I still love working here, is because you can show people uncomfortable analysis, and the vast majority of people will say, huh, that's interesting, I got to think about that a little longer. And so I think, you know, just do the analysis, right? Put it out there, right? John Hubble, right? John Hubble didn't just follow the leadership directives, he figured out that there was an easier way to get to the moon. And he sent letters to NASA headquarters all the time saying, hey, you guys are thinking about a different, you know, you guys aren't doing this the simplest way possible, right? Lunar orbit rendezvous, we got to give it a real look. And it was not a comfortable solution, right? Werner von Braun had other ideas because he wanted to build up an infrastructure in low Earth orbit that doing Lunar Orbit Rendezvous didn't enable. But he kept sending those notes, and I'll be clear, we get lots of letters from the centers of that type to this day at NASA headquarters. So keep writing them. I mean, that's all I'd say. I mean, if you think you've got the right hunch on some technical solution that people aren't seeing, keep pushing on it.
Any other questions? Yes. Hold on, I'll bring the mic. Stay right there, you can sit down.
Hello, my name is Jay Foster, and I spent 32 years in the space program. The first 5 years was the Army before there was a NASA here at Marshall. I just have a comment that you might comment on. One of the big problems, obviously, is how do we get money and get financing from somewhere other than NASA? And I recently saw this, what I think was a pretty dumb movie called Ad Astra. Yeah.
What did you really think, though?
It's just so far from reality. The question really is would there be a way to partnership with the movie industry, at least one time, to build a movie that would really get a lot of interest, that would be reality from some of the things we saw here today? Make a movie that's as close to reality as we can get, as opposed to, well, they showed a picture of the moon there with, I don't know, high-rise buildings and big cities on the moon, and
And
that's a
Applebee's,
little
too, if I
far from
remember correctly.
reality today. Just a thought.
Yeah. Any comments, Corky?
Thank you for that comment.
I
Anybody else want to
I just want to say I
comment on?
agree. I mean, NASA works a lot, as I'm sure you know, with Hollywood on a lot of these ones. Not a lot on Ad Astra, I might admit. There's a lot of folks who've been looking at those business models. As you may remember, Mir Corp back in the day was looking at that exact model for doing missions to the Mir space station. And I certainly know a lot of folks in the private sector who are simply looking at the costs, and they're waiting for the cost for actual spaceflight to come down to the point where you can actually do those films. And I think as long as the cost decreases, I think we're going to get to that day. So I think we owe a lot to the movie industry to shape these visions of where we're going, and I think we're going to have to keep working with them for decades into the future.
No, I think it's a neat idea. And, we did work very closely on the movie The Martian. Jim Green was an advisor, and they tried to make that as realistic as they could. Jim Green's now the agency chief scientist. But no, I think it's a great idea. I worked on the shuttle program for a long time, and this is my personal opinion. This is not a NASA opinion. I want to make that very clear up front. I thought it'd be cool if we could sell Budweiser to paint the external tank like a Budweiser can or a Coke can. I thought, yeah, that'd be great. And I think, who was it? Might have been George Carlin. They said, I really love the space program, and I think we ought to make every American just like they do when they go play video games, just, go put quarters in that so we can fund the space program. But yeah, that's a great idea. I wish something like that, could happen. And, to an extent, that is happening in the public-private partnerships, because when we say a partnership, it is a true partnership. Yes, NASA puts in money, but the companies also put in money looking for that commercial return on their investment. So that's helped the agency dollars go a lot farther, which is really helping us in the exploration program go to the moon.
And Alex and Corky, you guys represent, two of the thousands of people here at the Marshall Space Flight Center and in NASA headquarters, and the thousands of NASA employees across the country. We're only going to get there because of the great work that you two gentlemen do and the whole NASA team. So let's give them a round of applause. Thank you, guys. And stay here 1 second. If I could call up our team leads again, come on up here. I just want to give everybody here a round of applause to all of our speakers tonight. We hope you were as inspired as I was here tonight. I think the enthusiasm and to hear what's going on is really exciting. And again, it's hard to go there, and we're not going to go one person, one team. We need everybody. We need all of you. We need the great NASA employees. And with that team and the spirit, and I think the drive that everybody here has, and I think everybody in the audience, we're going to get there. And we're going to be sending the young students, they had to get to bed, but we're going to be sending, those are the Martian, the Mars generation. We're going to be sending them to Mars, and we see some of our Mars generation here still with us tonight. And this is why we're doing this. We want to go to Mars. We want to send you there, and you see, you're going to have great houses up there, nicer than my house, here on Earth. And we're going to have people taking care of you, watching out for your safety, and you're going to be carrying the torch. And that's what this series is about here, carrying the torch, passing the torch. We're passing it on to their generation then. Thank you all for being here tonight. Thank you.